In this video, we're going to talk about a nonlinear behavior in op-amps called slewing, which creates an important op-amp specification called slew rate. This is a deviation from our usual practice of confining our discussion to strictly linear approximations. We're going to start describing this slewing behavior by imagining that we've configured an op-amp for unity gain and we're putting a high-frequency sine wave into our unity gain buffer input. If we do that, our output won't look like a sine wave, which is a nonlinear behavior. A linear system always has a sinusoid out when you put a sinusoid in. Instead, we'll see a triangle wave that has some small curves at the top, and this triangle wave is probably going to be smaller amplitude than the input sine wave. We can also see slewing if we put a step input with a big amplitude into our unity gain buffer. Our response will be a straight line with a tiny exponential at the end. Again, this is not linear because a linear response to a step is a decaying exponential the whole time. A linear response wouldn't have this straight line at the start. However, this response does appear to enter something that looks like a linear settling regime at the end of the straight line because there's a short exponential at the top. Similarly, this curvy bit might be linear behavior if it's a little sine wave. Looking at these two responses, you might notice that they both have straight lines in them, there and there. And the slope of those straight lines is called the slew rate, and it represents the op-amp output changing as fast as it possibly can. So saying that another way, the slew rate is a speed limit on dVo dt, and it has units of volts per second as a result. It's the fastest change in output voltage we can get. And one detail that's worth noting here is that volts per second is the same units as amps per farad, because amps are coulombs per second and farads are coulombs per volt. Okay, so how do we get this volts per second speed limit? The answer has to do with the fact that some op-amp stages can only provide limited current. For example, the output stage might have some maximum current it can provide, and if that maximum current is being driven into a load capacitor, then the fastest the load capacitor can change is I out over CL. Remember, current over capacitance has the units of volts per second that we're looking for here. And there's some physics intuition for that too, right? That's as quick as we can shove charge into the capacitor. So this output current can limit the slew rate, but it's uncommon because op-amp output stages are generally able to drive a lot of current. It's much more common for the slew rate to be limited by the differential stage and the compensation capacitor. So the differential stage has a tail current, and one of the defining features of emitter-coupled pairs is that they steer the tail current one way or the other. However, once a tail current is fully steered, there's no way to drive the differential stage harder. At best, it can provide its tail current to a cap. And the compensation capacitor is a big cap that needs to be charged up in order to move the differential stage output node. I've shown IT being drawn out of this node, which indicates that the differential stage is steered fully to the right. There are some subtleties in how this current results in a change in the output voltage. Let's call the differential stage output V1 and the level shift output V2. Because there are no dynamics in the output stage, VO will exactly track V2, so if V2 is slew limited, then so is VO. Now, V1 is set entirely by the difference between the inputs, which in turn is set by how quickly VO can move, because V minus is a function of the output, because op-amps are used in feedback. That means for big input change, V1 is pinned until VO can catch up to V plus and start reducing the differential mode applied to the input. So after an input that fully steers the differential stage, V1 stays the same, and all of IT passes through CC. Because V2 is equal to V1 plus the voltage across CC, so charge times capacitance. That means V2 is going to change linearly with time as this current runs through CC. So our slew rate is set by I tail over CC when we have a mirror-loaded differential stage. One final subtlety, the slew rate changes when the differential amplifier is resistive loaded instead of mirror loaded. When a stage is resistive loaded, some current has to flow through the resistor in order to set the value of V1 here. So before a big slewing step, the current in the load resistor is IT over 2 because where differential stage is balanced. After a big slewing step, V1 can't change right away because VO needs to catch up in order to affect the change in V1. So that means IT over 2 has to stay in this resistor because V1 isn't changing. As a result, only IT over 2 is available to discharge the compensation capacitor. So, in summary, only half the tail current can get to the compensation capacitor because the other half has to pass through the load resistor to maintain V1. So this lets a third possible slew condition, the slew rate that's compensation capacitor limited with a resistive load, which is I tail over 2 CC. So in summary, op-amps can enter into a nonlinear regime called slewing, and when the output voltage is asked to change too fast. So dV out dt has a speed limit called the slew rate. The max change in the output voltage, the max rate of change in the output voltage is called the slew rate, and it has units of voltage per second. And the slew rate can be set by the output current or by the charging of the compensation capacitor. And the rate at which the compensation capacitor can be charged depends on whether we have a mirror load or a resistor load.